Okay, so welcome everybody to this afternoon's webinar from the Source ARC. My name is Michael Crawford. I'm the Chief Executive Officer of the Source ARC and your host for this session on new products for subsoil constraints. Firstly, I'd like to acknowledge the traditional owners of the land on which we are meeting today, wherever we are in Australia, and I'll pay my respects to their elders past, present and emerging. Now, we have a large number of attendees or registrations for today's webinar, and I know looking through the names, some of you are relatively new to the Source ARC, so just a couple of words about who we are and what we're about. So essentially, as a CRC, a cooperative research centre, is about bringing research and industry together. In our case, it's about agriculture and research. It's around soils and how we can undertake R&D to give farmers the tools and knowledge they need to better manage their soils and in turn improve and increase their productivity and profitability. We are funded by the Australian government and by our partners. We have support for 10 years. We're now just into our 5th year of our 10-year program. We have 40 partners across the country, including 8 universities, 4 state government agencies, 8 industry groups, and importantly, 20 grower groups and farmer groups involved in the Source ARC. We have a large portfolio of projects, especially now in reaching a very busy period in the lifetime of the CRC. And through this webinar series, we're giving regular updates on the research that we're undertaking and some of the results that are emerging. We've got today's webinar, which I'll come back to in a minute. Just looking at what's coming up. In 2 weeks' time, we've got a webinar by Dr. Amanda Sapol from PIRSA, Primary Season Region, South Australia, looking at improving the performance of sandy soils, a project that's led by Richard Bell at Murdoch University in Western Australia, but involves activities across Western Australia and South Australia. And then on the 5th of October, we've got Dr. Craig Lobsey from the University of Southern Queensland giving an update on some of his research about new sensors for measuring soil. Both of those webinars are at midday. Australian Eastern Standard Time, that is, in the first one, and then daylight saving kicks in, so Australian Eastern Daylight Time in the October one. Both those webinars you can register as you did for this one via the Source CRC website. And on the topic of websites and social media, yes, please look at our website. You'll get a big overview of what's happening in the Source CRC, the projects, etc., our partners. You can follow us on Twitter at Source CRC. You can connect with us at LinkedIn, Source CRC, and you can subscribe to our YouTube channel at Source CRC. And on our YouTube channel, indeed on our website as well, you'll be able to find recordings of this webinar in the next day or two, and all our past webinars as well. So there's quite a host of material there for you to look at and get regular updates. You can subscribe to our newsletter, etc. Today's webinar is on new products for subsoil constraints, and it's been delivered by Dr. Ehsan Tavakkoli of New South Wales Department of Primary Industries. Ehsan leads a number of projects in the Source CRC, as well as projects elsewhere led by, funded by GRDC and other organisations. He's a senior research scientist at New South Wales DPI at Wagga Wagga Agricultural Institute. He has over 15 years of experience and specialises in soil plant interactions, soil chemistry, nanogeochemistry, and a particular focus on soil-based constraints, especially in grain crops and farming systems. He's previously worked at the University of Southern Queensland, University of South Australia, and the University of Adelaide, where he undertook his PhD at the Wade campus there. So, without further ado, I will hand over to Ehsan to deliver today's webinar on new products for subsoil constraints. Thank you, Ehsan.
Good afternoon, everyone. Thank you, Michael, and thanks to Source CRC for the opportunity to be here today and provide an overview of one of the projects that we are developing for innovative approaches to improve subsoil constraints. So basically, first of all, I would like to talk about the size of the issue with the subsoil constraints. And namely, what we are trying to focus here is on sodic soils, acidic soils, and to some extent, salinity and saline soils. And if you look at these three maps, basically, the maps are highlighting the spread of the issue in terms of the yield gap that can occur in different farming systems from the northern region to the southeast and to the wheat belt of Western Australia, and how some of these constraints in farming system can lead into significant loss in production for Australian farming systems. So some examples are given here, which is basically about $1,300 million per year loss in production, for example, is associated with the issues of sodic soils, and then $440 million per year for acidic soils. Over the past few decades, Australian farmers have been able to tackle some of these issues when it happens in the topsoil. And now we are in a point that if we want to have any new frontiers to improve productivity, we have to start looking at what are the options to unlock the yield potential by improving or re-engineering the subsoil, because many of these constraints, when it happens in the subsoil, it's very difficult and challenging to tackle. And the current existing management options are not really effective in improving any of the issues when it happens in the subsoil. And hence, there are a number of approaches that we can discuss. Genetic solution, coming up with crops that are more tolerant to these hostile conditions, is one option. Having management options such as re-engineering the subsoils or new products is another option to tackle the soil constraints, or specifically subsoil constraints in farming system, which I will discuss today. So soil acidity, very quickly, just talk about what is the problem with acidic soils. Low pH, pretty much below 4.8, and aluminium toxicity in those pH conditions is responsible for the yield declines in acidic soil, and it's an issue that basically, if it happens in the subsoil, the surface applications of lawn is not going to be effective in addressing the problem in the subsoil. Some studies based on long-term field experiments shows that after you apply consecutive lawn application in the soil surface, it takes about 20 years to change the subsoil pH by 1 unit, and that clearly indicates that we need some innovative material or some innovative management options to improve acidic conditions when it occurs in the subsoil. But what can you see here in this image? On the left-hand side is the effect of that low pH associated with aluminium toxicity that basically start to impact the development of roots in wheat. And at the field escape level, in the paddock, you can have basically complete failure of the crop if that aluminium toxicity is not going to be corrected by lime application, which you can see. So that is soil acidity. Another significant issue in the farming system in Australia is sodic soils, and there are a couple of issues with the structure of these sodic soils. Many of these sodic soils have dispersive behavior, which is basically due to a chemical imbalance of that exchangeable sodium as opposed to the other exchangeable cations such as calcium, which is responsible for maintaining the integrity and structure of the soil. And also the lack of organic carbon in these soils, especially in the subsoil, means that you have a lot of slaking occurring, which can cause significant issues for the collapse of that soil structure. And I refer to these soils as poorly structured subsoils. They have other issues such as poor nutrition, extremely high pH, which can have multiple effects on crop growth. And you often see one single application of gypsum, for example, that is known as a common industry practice, is not effective enough to correct the multiple constraints happening in these soils. Some graphical illustrations of the problem. This is on the left-hand side, you see a beautiful canola crop in Western Australia in a soil that is prone to waterlogging due to that heavy texture. And from a really good crop, which I call it a hero. It goes to zero in a matter of days after that waterlogged condition completely killed the crop. The image on the right-hand side is from New South Wales, and this is pretty much taken 2 days ago, where you can see severe crop failure affected by the rainfall, but it is really that infiltration, hydraulic property of the soil that doesn't let the water to infiltrate, and basically you come up with transient waterlogging conditions which can affect your crop productivity. Regardless of what the problem is, so there is one problem that happens across the farming system when you have subsoil constraints. Acidity, sodicity, salinity, all the concept of the work is improve water use efficiency. And if we are to improve the crop productivity and agricultural farming system, any approach should focus on what can we do with that bucket of water in the soil, especially in the subsoil, to make it more available and improve crop water use efficiency and basically start to see productivity impact. The current products in the market, for example, in here, I'll talk about lime very quickly. You have a range of different lime products, and they have a different quality, different neutralizing value. This is just a research paper that basically talks about the different effect of lime with different particle size on its capacity to change the soil pH. And that particle size plays an important role in how effective that lime could be in changing the soil pH and its capacity to actually move into the deeper soil profile. So in one of approaches for this project, we started to think about what are the current options that we could basically employ to manipulate the particle size of the product. Ball milling or assisted ball milling by using surfactant is a known technique that we can actually use at the industrial scale to achieve nanostructured lime. And so what is illustrated here in the image is basically different approaches that we could have in terms of surfactant and the product, which would be a lime or gypsum. And after grinding these product together with the surfactant assisted milling, we can have a functionalized product with a much more improved particle size and turn it into a very pretty much tailored product for different soil types. Either it's a sandy soil that has that acidity problem, or for example, a clay soil in southern New South Wales with acidity problem, which the size of the particle and the functionality of the surface lime, the surface particle could be used to improve its behavior and mode of action in different soils. So from that, this is the work that we have done recently using different milling techniques. Attrition milling is being compared to bead milling and also planetary ball milling. And for this system to be feasible in terms of larger scale production of the product, it has to be low energy, and also it has to be relatively fast. And the recent and the quick work that we've done in this space basically show that attrition milling could be useful for achieving that really small particle size of up to 300 nanometer for for gypsum, and also 400 nanometer for lime. And just to compare to existing products, you are talking about a product that commercially is available with a particle size of 80 to 100 microns. So that is 80,000 nanometer. So the change in the behavior of that particle size is actually quite remarkable. A very quick demonstrations of what it means for the actual change in the chemistry of these products when you put them into a solution. So here I just compared one of the nanostructured lime that we synthesized in the lab with an ag lime. And so the orange dots here is the ag lime, and the gray dots are the nano lime. And you can see from the kinetics point of view, you have an improved dissolutions of calcium from the nano lime as opposed to ag lime. And the changes in soil pH also, in here is a solution-based study, is also a lot more improved in that nano lime as opposed to ag lime. And if I just focus on at the onset of the experiment, where you're looking at the dissolution and reactivity of the new lime products with the nano structure, you see that the pH changes at about 5.7 or 6 for an ag lime, which is a commercial product, as opposed to an starting pH of 9 with our nanostructured lime, which has an important implications for its reactivity in the soil environment. From here, we did some soil-based study in soil columns in the lab with surface application of ag lime and comparing them with the best products that we could synthesize in the lab. Very quickly, the pH profile of soil that you can see here in this graph is basically coming up at a topsoil pH of about 5.2, and then it reaches a subsoil pH of about 4.4 and 4.2. At that pH level, the aluminum toxicity could be significant. So any lime application would target to raise the pH from that 4.4, 4.2 to something at about above 5.2 to correct for the pH and correct for that aluminum toxicity, which I will show you in the next slide. So the surface applications of that ag lime had minimum effect on the subsoil pH. As you can see, we still have a pH of about 4.4, 4.2 in that depth of 10 or 15 centimeter. The same application that we looked at the nano lime in these two occasions, in these two examples, was able to actually shift the pH significantly from that low pH of 4.4 to about 4.8 and reaching that 5 scale. So what it actually means in terms of changing the aluminum toxicity is that very little changes in subsoil pH has a remarkable effect on correcting the aluminum toxicity, because the changes in aluminum speciation is based on thermodynamic equilibrium that you can achieve that correction for aluminum toxicity. Based on the current product that is commercially available, an ag lime with a particle size of, for example, 80 micron, we can see that we still have about 20% aluminum, exchangeable aluminum in that subsoil, whereas the correction in soil pH by the surface applications of nanolime reduced it to about 5% or less, which that 10% is the threshold for toxicity of aluminum to hurt the crop. From this, we did some plant-based experiment, and we can see some really nice effect about the effect of that surface applied ag lime on the rooting depths of the wheat crop in this occasion. And when you do the water use measurements over time, you see the cumulative water use is improved under that nanolime treatment as opposed to the ag lime. You will still see the benefit from ag lime as a comparison to control, but we have a better water use by the applications of nanolime, and that basically compares the effect of lime applications on the rooting depths coming from these new products. Some more photographic observations of this experiment. So basically this soil is from Ferndale, which is in southern New South Wales. The subsoil pH is about 4.3 with about 22% aluminum toxicity. So the surface applications of the nanolime, as you can see, affected the rooting depth significantly, but again in the favor of that nanolime as opposed to the ag lime. And we also looked at the subsurface applications of ag lime, because now we have the capacity to use our machinery to deep place the products if we want to, where the problem is in that subsoil. And still quantitatively, we have data that shows the nanolime promote the health of the crop and rooting depths, which is linked to the changes to soil chemistry. So that was just an overview of what we did with the ag lime and converting that to a better products if we can with the nanotechnology and achieving a better particle size. Another aspect of this project is looking at coming up with carbon-based, organic-based products for soil structure or sodic dispersive soils. And of course, BIOCHAR always has an application here to use the property of the unique properties that it has, but enhancing those properties to have a bespoke, a specialized design product for different purposes in farming system. This work has been done in collaboration with a number of scientists, and what I will report is basically looking at sodic dispersive soils and that have problem with soil structure. So basically, we use the raw biochar, which we could actually control the surface functionality of the product by the temperature of the pyrolysis, but more importantly, by embedding different minerals and additives in pre-treatment or post-treatment to the product to make it a completely different innovative amendment, which I call it a carbon-coated mineral, because the behavior and characteristics of that is very different from a raw biochar after you change and modify those properties. A focus would be on the redox properties of these amendments, because we do have now quite a large amount of data that shows the electron shuttling transfer and redox property can actually interact with the crop productivity and soil behavior to improve the system. So some macroscopic characterization of the work of the biochar that, for example, we produce here. You can see that the nanoparticles of some of the minerals that we use, for example, calcium-rich minerals, are embedded into the pores of biochar, and then it shows that we actually achieve embedding or filling those pores with the minerals that we are interested to use for different soil types. And from there, we go to a number of glasshouse-based experiments to look at the crop response, but also more importantly, to actually look at the link between that electron transfer mechanisms and crop productivity. And these are some of the examples of work that we are doing in the glasshouse right now and run by my team in Wagga Wagga Ag Institute. So some quick examples of some of the responses that we get from the soil. So as I mentioned, the images that you get here on the top left-hand side is 2 biochars, which is filled with selected minerals that we come up with the formulations. Again, pretty much those minerals are at the nanoscale, and we get responses to improving soil dispersion, as you can see in that Petri dish, for example, from left to right, with increasing rate of applications of the amendments, that dispersive behavior could be settled. And when you do pot experiment, we can actually start to see significant improvements in the soil structure of amended soil as opposed to control. To show it into a more representative way, this is an experiment that has been done by my colleague, Dr. Shahabuddin in Wagga Wagga Ag Institute, and basically looking at the effect of amendment applications in the subsoil on a wheat crop, where the productivity could be manipulated and as opposed to the control or non-amended solid subsoil, which has also high pH. So we have started to see some of these productivity measures, which is quite encouraging using these novel, innovative ideas. Another aspect of this work is the collaboration that we are doing with other projects, and an example here that I'm going to provide is the Calcutta Soils project that is co-funded between GRDC and Soil CRC, and we are also involved in this project. And I think this program 3 project has been quite useful in developing products, which is servicing some of the other projects. So the start is always with a good coffee and conversation with wise man, and in this case is Dr. Lucas van Zwieten, my colleague at Bollenbar Ag Institute. From that discussion, this leads to synthesis and development of the formulations that we come up. And then its characterization is very important because we want to know what have we achieved with that new formulation, okay? And chemical and also morphological characterization is a big, quite an important, significant part of our research. From this work, we go to brainstorming and setting up experiments in the lab, and we always have something between 10 or different amendments that we need to screen in a high throughput screening system. And this particular product that we developed for the Calcutta soils to improve some of their hostile condition showed significant improvements in that crop biomass in the soil that we got from South Australia. We also is very aware of the nutritional value of these products to make sure that whatever we add into the soil is not just nutrition. So we are matching the P or N content of the products with the total amount as a fertilizer. And in this case, we actually had up to 40% improvements in plant productivity as a comparison to control, which was also matched with the P treatment. So that was quite encouraging. We also have close industry collaboration, and we are able now to bulk produce these products at the larger scale. And this is one of the colleagues that we work with in carbon-powered mineral technology based in Tambors, and with some of the minerals that are coming from the mine. In this case, is a basalt deposit that could be used for enhancing the redox properties of some of these biochar. we are able to bulk reduce some of these. The end product is a pelletized biochar, which is highly soluble, and also it's ready for field application. So going to the calcareous, so we always reverse engineer what the problem is, and we had a lot of large discussion with Nigel Wilhelm and their colleagues from Sardi, and based on the problems that are basically really high pH in the soil, lack of organic carbon, and some nutritional problem, which is in this case phosphorus, we looked at the applications of this product in the field. This photo was taken by Brian and sent to me a couple of weeks ago, and basically 16th of August 2021, where we can see some encouraging responses from the carbon-coated mineral with enhanced redox property, and we focused on soil pH and phosphorus. So just to give you an indication that according to Nigel, most of the growing season, these crops are phosphorus deficient, and any improvement in that avenue of phosphorus nutrition could actually have large outcome for crop productivity point of view. Another example in a different field site, again in the calcareous in Port Guinea, we can also see some nice responses so far to that product that was applied a few months ago in this experiment, and we are looking to see what it means for the production. We are going into some further studies in the future, so a number of other avenues for developing products with our colleagues, and also we are at the point that we would like to do field validation with the machinery and precise applications of these products in the field, either the surface applications or in the subsoil. And with that, I think this is the most important actually a slide of the presentation, because it's all about the people and the brains and the talent that has been contributing to our work over the last couple of years. And I really would love to acknowledge the contributions of many people from DPI, University of New South Wales, and University of Newcastle, and of course the funding from Soil CRC that enabled us to come up with some of these innovative research, in my opinion. Thank you very much.
Thank you, Ehsan, for that very interesting presentation. Now you can see Ehsan's email address there, so you can follow up and ask him questions after this event. But what we've got now is about 15 minutes of questions and answers. So the opportunity is there for all participants, all attendees to ask questions. Ask questions by typing them into the Q&A box, and I'll be able to, Ehsan and myself, will be able to see them, read them, answer them. And if there's questions there that you're particularly, you can ask the same question, you can upvote it so it goes to the top of the list. Now, I'm not seeing any questions there at this stage, so I'll just couple of questions coming into the chat box, so we'll start there, but try and put it into the Q&A box if you can. So it's a question from Bill Adams there saying, what rates of nano-lime compared to ag lime? So if you're using nano-lime, same rates, or do you do it differently?
Yeah, sure. No, we did rate a study as well, and basically I can tell it's about 35% less lime application is needed when you use nano-lime because it's more effective. So if you use 1 ton of each, you actually need 30% less of the nano-lime so far. So that is based on the preliminary rate study that I've done with this work. And that's one of the really important economic point of view for these products, because some of them are, if their efficiency is a lot higher than the conventional products, so you don't need to apply as much as you usually add in the farming system.
Good. So I think Bill's just followed up. He said 30% less, question mark. Can you see that?
Yes, that is correct. Yes.
Okay. Andy McNeil's asked, do you plan to do some economics on the cost benefit from these enhanced expensive products?
That is, I think, the most important question that I always get. Yes. For me, the important stage one was to come up with a proof of concept. And I'll give you an example. After talking to Nigel for the phosphorus situation, we wanted to demonstrate there is a tangible product or a proof of concept that can effectively address phosphorus nutrition in a really hostile condition, for example. Or can we improve the dispersion of a subsoil or subsoil acidity issue with the surface applications of lime. And the next stage would be the commercializations and also cost analysis. And with any other new products, I think when you talk about larger scale production, the economics of these will be coming down significantly. No, undoubtedly, I think there will be a bit of cost involved in setting up and manufacturing and the infrastructure that might be needed. But the proof of concept is promising, and I think, yeah, we really need to do an economic analysis of this product and their longevity in the system, because with some of these organic-based products, it's a one-off application, which I'm expecting to carry a number of years of residual effect in the farming system, which needs to be considered.
Right, good, thank you. I got a question from Mick Rose, excellent presentation. Just wondering about the responses in the pot trial to the nanoline. How long did it take for those differences to show at depth, i.e. greater than 10 centimetres, and what kind of watering regime was used?
Yeah, great question. 7 weeks. So the changes in soil pH, we were able to show that that can be manipulated in 7 weeks. The water content of the pot experiment, and just to bear in mind, we are using large columns, 60 to 80 centimeters columns. We were usually maintain the water at about 60 to 70% fuel capacity, or sometimes at 80 fuel capacity. So it's not an unrealistic watering regime, and most of the time we stop watering if we grow the plants for the whole period. We stop the watering from flowering times to mimic what happens in the field as much as we could. So the transport and mobility of the particles is not being extremely affected by the watering or aggressive watering events. And it's really, I think, in my opinion, to the particle size of the lime or gypsum product that can migrate into the subsoil. And by surface application, I just want to make myself correct. We are actually mixing it in the top 0 to 2.5 centimeters. So that could be a very shallow incorporation flow, just to get that first activity.
Okay, thank you. So Lucas has asked, Ehsan, what is the appetite amongst growers for amelioration of subsoils?
Look, 10 years ago, if I was talking about this, many people would laugh at us because the cost of doing such a work right now is a bit inflated with the increasing price of land and the fact that the farming soil is an asset for the farmers, and looking after it and improve productivity. Just buying more land is not anymore an option. The appetite has raised significantly. In southern New South Wales, there are a number of farmers that are adopting, focusing and investing in subsoil machinery, for example, to start implementing some of these amendments into the subsoil. And the appetite is high, so that's why there is a bit of desirability and feasibility for this sort of work to be continued. The important thing to mention here is that solution for different soil type has to be tailored to what the problem is in the subsoil. So just organic matter or gypsum or lime is not going to be, or it's not the answer always to different soil. So every farmer has to understand and diagnose what the problem is, and based on that, definitely if you can show avenues for productivity, the adoption of this work is really high. The rate of adoption and the appetite for it is really high.
Good. So there's a question from Andy Bates, which has got 2 upvotes, so people want this one answered. In the calcareous soils, what is the mechanism causing increased phosphorus efficiency from the biochar products?
Okay, so that's a very good question, and this is some of the more fundamental study that I need to do together with a number of people. But the idea and the concept of electron shuttling and having a biochar which can have a lot of functional groups on it is proven now, and there's a lot of mounting evidence that it can show we can unlock and make this phosphorus more available when you have it embedded into a biochar with the enhanced redox properties. And based on that electron shuttling mechanism, your crop will be able to see more of that phosphorus as opposed to conventional treatments. The interesting observation in that calcareous soils is that when they added phosphorus at the same level as in the form of phos acid, for example, you will still see your crop is suffering from nutritional values as opposed to a biochar enriched phosphorus, which that mechanism could probably contributing towards unlocking some of that nutritional value.
Okay, Tony Paddy has asked, well, great talk. One of your biochars showed significant chromium levels. Is this coming from added basalt minerals and presumably not bioavailable?
No, this is due to the coating of the, it's a SEM image, and then we are measuring the different things on that biochar. We're mounting it with chromium. So that chromium coating to fix the sample for introduction to a scanning electron microscope comes as the chromium peak. It's not in the biochar.
So it's an artifact. Okay.
Yeah.
All right. Important question when it comes to the end, or comes to its use. So Brad's asked, are there any suppliers of nano lime and gypsum?
Look, there are a couple of products that they are being sold as nano gypsum or nano lime. I've seen it. It's liquid in liquid form. Look, when it comes to nanotechnology, there are a lot of products that when you buy off the shelf, they are being claimed as nano products. When you do the actual characterizations, they are actually into submicron or micronized size, and they are no longer nano. And that's one of the problems with to make sure a nano solution or nano product is staying in nano form. There's quite a bit of different artifact there that contribute to the problem. But to the best of my knowledge, a tangible, really nano lime product or nano gypsum product is not available. There are nano-based fertilizers that's being sold in the market, and they are nano. But yeah, so from the amendment point of view, I don't think commercially there is anything right now available that could be claimed really as a nano-structured amendment yet.
But as this research continues, and if and as we demonstrate the efficacy of this approach, that supplier market might develop.
Absolutely, and exactly, that's pathway to market from the research results that we've got so far to the next phase.
Which is probably a bit related to Rob Norton's question. Great talk, Ehsan. What can you say about the handling properties of nano lime?
Yeah, no, that's good. Look, the nano lime, so if we do surfactant assisted milling, for example, to come up with the lime, we can also come up with pellets, or we can come up with a granular of lime that the coating will be dissolved in the water as soon as it's being introduced, because you are right, a nano powder is very difficult to spread in the field, but with the powder technology, you can absolutely manipulate its application.
Okay, David Hine has asked, it's a very useful presentation. Would you regard subsoil physical conditions to be the top constraints on productivity?
Absolutely. Soil structure is directly affects your water relation, and that bucket size, the amount of water that you can make available to the crop to have a productive or unproductive cropping season definitely is one of the measures of productivity. So soil structure, however, as I say, is connected to the chemistry as well, because in dispersive soil, it is that exchangeable sodium and the net dispersive charge that causes dispersion. And also you've got the problem with the lack of carbon that causes the slaking, or you can have also a very heavy soil with our 70% clay topsoils. And improving that structure, which is in one of our upcoming projects through the soil CRC, we are trying to develop amendments to improve the porosity, aggregation, and the structure of these soils. I think would be one of the major contributors to productivity in dryland farming systems.
Agreed. Okay, so Terry Rose has asked, what was the pH of the biochar applied to the alkaline soil?
Okay, that's good. It was about 4.8, Terry, and the post-treatment with phosphoric acid, in addition to making that phosphorus embedded into the pores of biochar, it also means that you come up with an acidic or highly acidic biochar, and we did it in purpose because we wanted to correct the pH of those highly alkaline soils in the calcareous soils of South Australia. So, and you can manipulate that as much as you want, really. So you can add some other functional groups that have more acidification values in there. But 4.8 wasn't that particular product.
Thanks, Ehsan. Now, there's no more questions in the Q&A box, and so there's opportunity still. We've got a few more minutes if people have got something else to ask. I'll just go to the chat box. There's a couple of comments and questions I'll pick up here. Naomi Schultz is the exec officer with Air Peninsula, one of the grower groups in the soil CRC. She said that the Western Eyre Peninsula farmers have been very excited to see the treatment responses in the calcareous soil trials at BIOCHAR, Port Kenny and Minapa by Ehsan. So I'll turn that into an opportunity for you to comment, Ehsan, about the engagement of the grower groups and farmers in your research here.
Look, in my opinion, and the research that we've been conducting in DPI, it has to be always based on a clear farmer demand, and with that amendments and product, it has to be feasible, desirable, and it comes back to the question that Lucas asked, whether this work and improving subsoil constraint is an area of focus or interest for the farmers. So farmers' engagement over the last 6 years has always led us to what is the problem and how we can improve it. And there are endless number of conversations we have with the farmers in different farming systems. And in another project that is done through the soil CRC, we're looking at water use efficiency in those. You know, the sugarcane industry, for example, they've got some really significant issues with the soil structure that I reckon some of these innovative products have a major role to play in that system. Grower groups has always been very educational for us as well, Michael. So, you know, linking to different states, the work that we do with Western Australia, with New South Wales, Victoria, and South Australia, they're always being led and informed by what the grower groups are actually listing as their top priority to improve their system. And some of the products that we are developing as a new generations of lime products will be used in demonstration sites that Riverine Plains will be setting up later this year for their grower groups. So,
yeah, thanks, Ehsan. I probably did ask as a bit of a Dorothy Dixon. It also highlights that even though you're working in New South Wales DPI, through your collaborations in the soil CRC nationwide, we're able to have that impact across state borders. And
well, I need to be careful over Lucas that the primary benefits of research should be for New South Wales because of my commitment and our commitment to New South Wales. But the issues in farming system is spread over the whole nation, and I think the problem that are at the moment in a different dryland farming system is in common between northern, western, and southern regions. So,
yeah, it's good to see a national collaboration across the states. It's not happening in some other areas of life at the moment. Listen, we're coming up to 12:45. There's a few questions that are still there. I'm going to call it quits because this was the advertised time. And so, Ehsan, we've got a record of those questions. Ehsan will be able to follow up by email afterwards. So, thanks everyone for your participation. I hope you got a little bit out of it, and you have the opportunity to follow up with Ehsan if you need to. Just to finish off, I'll come back to our website, our Twitter, our LinkedIn, our YouTube. You can watch a recording of this webinar in a couple of days' time. You can connect with us through our newsletter and with other activities that are happening in this project and others. So without further ado, thank you everyone for your attendance. Thank you, Ehsan, for a fantastic presentation, and wish you well for the rest of the day, and hope to see many of you again in 2 weeks' time. Thank you.
Thank you.